So similar to the descriptive statistics for the categorical variables where you report the number and the percent, for continuous variables you report both mean and standard deviation. How to calculate the mean and the standard deviation? Let us go to the data. Again, you go to analyze. I'm doing descriptive statistics, and there are two places where I can do these. The first place is descriptives, okay? And even if you look here at the icon or at the picture, it shows you the symbol of the mean and the symbol of the standard deviation, okay? It is showing you that this is selected whenever you want to calculate the mean and the standard deviation. If you select that, again, all the variables that you want, what I can do is I can select all the continuous variables, right? This is not a continuous variable, but I forgot to change it when I calculated the marital status. So I'll skip it. The weight, the height, the body mass index, just I can be able to just look at the symbol and be able to see which variables I need to include. All of the continuous variables and duration of emergency stay, and I click on OK. So again, in one step, you get all the results for the continuous variables. And here you see that age, you have 288 people, minimum is 19, maximum is 85, the average is 52.6, and the standard deviation is 12.9. Okay, so in one step, I was able to get all the descriptive statistics for all the continuous variables in my data set. Fine. So what I do now, I take these numbers and we summarize that the mean and the standard deviation are the two numbers that you should take and report in the paper or the report. Now, what are the graphs? The graphs are not the bar chart and the pie chart. We call it a histogram. Now, how do we do the histogram? When we went to the frequency distributions and we went to the charts, there was a histogram. You see it here? So there is a histogram. You can click on it, continue, but I don't want these categorical variables. I want the continuous variables, so I'm going to select the age, weight, height, BMI, and then this heart rate at admission, discharge, and so on and so forth. And I click on OK. What's annoying in this is that it will give me a long list of all the tables that I do not want, right? I don't care about them. I'll delete all of them and show you how can I get rid of it, which is descriptive, frequencies. I uncheck this box, which is display frequency tables, and I click on OK. And now I will be able to get all the histograms for all the continuous variables. Okay? The same thing, I can double click, open the chart editor, modify anything I want, and then copy and paste in my Microsoft Word document or any PowerPoint presentation or whatever. Now, somebody might ask, what if I want to calculate the median and the interquartile range? I'll go to Analyze, Descriptive, Descriptives. There is an Options button. If I click on Options, there is some other things that you can calculate, but median is not there. You can ask for the variance, for the range, but median, mode, and so on and so forth are not there. So there should be another way to do it. How do I do it? Again, by Analyze, Descriptive, Frequencies. Although this is for categorical variables, but if you go to Statistics, look at this. You have the central tendency that I told you about, which is the mean, median, mode. You have the dispersion that I told you about, which is standard deviation, variance, range, minimum and maximum. And even you have other things that I will tell you in a minute. I'll tell you about in a minute. You click on Continue. I do not want the frequency tables because they are continuous variables. I click on OK. And now I get a summary for all the variables that I have. So I have the mean for age, median for age, mode for age, standard deviation, variance, and so on for all these continuous variables. You might ask me, when do we report median and, let's say, range? I tell you, if your sample size is less than 30, it's better to report the median and the range rather than the mean and the standard deviation, and this is how you calculate it. Now, as a summary, or before I summarize it for you, graphs, legacy, you go for a histogram and you ask for the variable, let's say, duration of emergency stay. And I click, of course, you have the titles here, the modifications, and so on. And you click on this and you'll be able to find the duration of emergency department stay, and this is the frequency or the histogram for this variable. Okay? And as an interpretation, you see that a lot of people stay short period of time as compared to fewer people who stay longer in the emergency department, which is expected. As a summary for descriptive statistics, number one, descriptive statistics, you go to analyze descriptive statistics, and there are two things that you can do.
After hours.
Frequencies, which usually is done for categorical variables, and it gives you the number percent. Or you can ask for a continuous variable, remove the display frequency button, and you will get statistics, and you can select anything you want. The mean, median, and mode. And the third thing is that under descriptives, you can get briefly the mean and the standard deviation in a very concise manner. You have to know what is the graphs, legacy, whether bar, pie, and or a histogram. There's another one that we usually use called line chart, and it is done for continuous variables. And finally, one thing that I did not tell you about, which is the frequencies. Under statistics, you have the quartiles. The quartiles or percentiles in general is a if you ask for quartiles for age, for example, let me show you what it means. It gives you three numbers, meaning that the three numbers that divide your data into four equal parts. So quartile means 4. So when I say I want the quartiles, it means that I want three numbers that divide my data into 25%, 25%, 25%, and 25%. So you can see that 25% of the patients are less than 42 years of age. 50% are less than 52 years of age. And 75% are less than 62 years of age. Or you can say there's 25% between 42 and 52 years of age, and so on and so forth. We use these frequently in, for example, growth charts, where you say 95th percentile of weights for babies, or so on and so forth. So the point is, again, analyze descriptive frequencies, statistics. You can ask for quartiles. You might ask for 10 points equal groups. Let me show you what it means. If I want the SPSS to divide it into 10 equal groups, I'm asking for 9 numbers that divide the data into equal parts. So 10% are below 36 years, 20% are below 40 years, 30% are below 45 years, and so on and so forth. Okay? One last part is under statistics. Assume you do not want equal parts, you want the 95th percentile. Thus, it will tell you the 95th percentile for age is 75. What does it mean? 95% of the patients are less than 75 years of age. Okay? The percentiles, we do not use it very frequently, but I just wanted to give it to you so that you understand, because under statistics now, you will be able to know what the percentiles are, what the central tendency are, what the dispersion are. This way, you'll be able to get the frequency, not the frequency, you can get the descriptive statistics for any variable you have in mind, whether it's a categorical variable or whether it is a continuous variable. Now, one last thing I would like to highlight before we move into inferential statistics is the fact that although SPSS is a smart program, but it is at the same time, it's a stupid program. For a simple reason, you have to understand what you ask for. If you ask for the wrong thing, you might get the wrong thing. So let me ask you, or let me highlight something for you. If you say, I want to get the frequencies for age, you know that the chart that you should be getting is a histogram because it's a continuous variable. But at the same time, assume you do not know and you ask for a bar chart, SPSS still gives it to you. But no, I wanted to get a pie chart. So assume you do not know that the histogram is for continuous variable. You get a chart, but this chart means nothing. And usually I like to give this just to highlight that not everything you ask for might make sense. You are able now to see that this is not logical because it's very bad, right? You cannot make any sense of it. But what I want to highlight is that when you're talking about inferential statistics, about p-values and confidence intervals and t-tests and chi-squares and so on, you have to really understand what each test is used for. Otherwise, you might get a p-value, and I assume you know what a p-value is. You might get a p-value which is wrong, but you will not be able to see it, as you were able to see that this graph is wrong. So, as a summary, I would like you to know analyze descriptive both frequencies and descriptives to be able to do descriptive statistics and to be able to structure graphs for both categorical and continuous variables. Before I move into inferential statistics, I would like to highlight two things that we usually use a lot in SPSS, and these are split and select. Now, what does select mean? Assume that you have these patients, okay? And you would like to take into consideration only the married people. For some clinical reason which I do not know, you want only to take married people. So you want to ignore from your analysis everybody who is not married, okay? So in other words, I want to remove all these widowed and single, okay? And I want to remove all these who I do not know about their marital status. All of these I want to remove them, okay? How do I do that? Of course, you're not going to do it manually. You have to do it through the computer. What I do is I go to data. It's a data step. It's a data thing. I want to modify my data. So I click on data. There's something at the end called select cases. What does select cases mean? It means that don't take the 291 people into my analysis. I want to select specific people to be taken into my analysis. And I click on this button. By default, it is select all cases, meaning that all the 291 people will be taken into the analysis, and this is what has been happening in all the analysis that we were doing. But now I do not want to take the 291 people. I want to, if condition is satisfied. What is it if condition is satisfied? I click on if. What is the if? The marital status is equal to 1. I have to understand the coding here. I know that the coding 1 means married. So all what I'm telling the computer, select cases if the person's marital status is equal to 1. What does it mean? Ignore anybody who is not equal to 1. I click on on yes, and look what happens. Now it tells you if condition is satisfied and marital is equal to 1. I click on OK, and look, it says compute filter marital equal to 1. It means only marital is equal to 1 are taken. If you go to the data, look at this. You see these crosses? They are crossed now. Why? Because I told the computer remove these people for me because I do not know their marital status. And I told the computer remove these people for me because they are not married, single and widow. So this way, if I go to the average age, assume that I want to get the average age. I want those, but I do not want any charts. Who do you think will be included in the analysis? 263 patients, right? Why the 263 patients? Because I removed those who had missing information about their marital status and those who are single or widowed, right? So now everything that I do in my analysis will be restricted only among those who are married. Now the same thing, if I go and do frequencies, reset, for those who died, for example, I will be able to see out of the 266 people, 3.4% died, and 96.6% were discharged. When do I use that? I use it whenever I want to do secondary analysis. It means you have a clinical trial, a big clinical trial, multi-center, which was done in Lebanon and the States and in any other country, for example, and you want to do stratified analysis only among those who were in Lebanon. So I go and select patients who are only from Lebanon. Okay? The same thing. I might want to do a study on only males, only females, only young, only old, or whatever. But look at this. Assume that you want not marital status, you want the age. Age to be older than or equal to 35. Okay? I click on OK. I click on okay. I clicked on OK. Now age ascending. Anybody who had missing age will be deleted. Anybody who is less than 35 will be deleted. But what happened is that those who are less than 35 are still in the data. Okay? I did not exclude them. Look what I can do. Assume that you want to do something permanently. By default, it is filter out unselected cases. It means that keep those who are aged more than 35 in the data, but filter them out. Yani keep them in the data, but don't include them in the analysis. What I can do is I can delete unselected cases, meaning that those people who are crossed will be deleted from the data set. It's not a very good thing to do because you will lose them. A third point could be copy selected cases to a new data set, meaning that you will have the 5 MI times, but you can name another data set means 6 MI times more than 35 years of age. Thus you will have another data set, only those who are more than 35 years of age. Is it clear? Okay. So select cases is you can either select them permanently by deleting unselected, by copying the selected people into another data set, or keeping them into the data set but crossing them, not being included in the analysis. If I want to remove the selection, I put reset and everything goes back to all cases. Okay, and now everybody is selected. This is the first thing I wanted to tell you, which is select cases. The second thing I want to tell you about is the split file. What does split file mean? Most of the analysis that you do, you would like to compare. So for example, you want to compare males and females according to their systolic blood pressure, or males and females according to their discharge information, or smoking status, or body mass index, or whatever. So if assume that I want to get the body mass index for males and for females, what I can do is I can go to data, select, and if condition is satisfied, males, like this. I put sex is equal to 1, meaning that only males are selected, and then I go to analyze, descriptives, reset, and I want to go to BMI. What am I doing? I'm getting the average BMI. Is it for everybody? No, for 240 people. Who are these 240 people? The males. So what's the average? 22.58. What's the standard deviation? 7.6. What about females? I go to data, select. If condition is satisfied, I select 2. Continue, and OK. Analyze, descriptives, and now how many people are included? 44. Who are the 44? The females. What is their average? 21. So you can see that males have a higher body mass index as compared to females, right? But I'm doing the same thing more than once. Instead of doing it like this, selecting males and getting the average and selecting females and getting the average, I can tell the computer, split it for me. But before I split, I'll go to select and reset so that everybody will be included. I go to data, split file. You see the icon here? This is a data set, but there's a line between them. as if I'm telling the computer, don't use everybody together. Split it for me. In other words, give me analysis for one group and for another group separately. What do? Split. By default, again, like all the other analyses that we have done, analyze all cases, do not create groups. I can select organize output by groups. What is the group that I want to do? Sex. So now, again, read. Split file and organize the output by groups, and the groups are based on the sex of the patient. So any analysis that I will do now, it will be split into males and females alone. Let us look at what happens. Nothing happens because I did not exclude anybody. It's an internal command that I gave to SPSS that anything I ask you, split it for me. I analyze, descriptive, descriptives, and I click on OK. The output will not be for 291 or 291 people. It will be for 240 and 44. Who are the 240? The males. 44, females. The same numbers, 22.5, 21.5. But instead of doing it in multiple steps, this is what I have. The same thing, I can go to data, split files, assume that I want to compare those who died and those who were discharged. I click on on OK. I analyze, descriptive, descriptives, and I'll put age. Why am I doing this? I want to see the average age for those who died and the average age for those who survived. So I split according to final outcome, death, final outcome, discharged. So 10 people died, 276 were alive. Average was 59 for those who died. Average was 52 for those who were discharged. I can see that those who died are older. So in one step, I was able to tell the computer, give me the results based on two different groups. Those who died and those who did not die. I'll delete everything. Now, whenever this is activated, any analysis that I will do, even for graphs, let's say, assume that I want to get a bar graph for the not final outcome, because I split according to final outcome, according to hypertension. I click on OK, and now I have three graphs. One is for missing. You see it here. Final outcome missing. I don't care about it. Final outcome died, and final outcome discharged. So this is the hypertension status for those who were alive. This is the hypertension status for those who died. Again, any analysis that I will do from now on, it will be split according to the final outcome. I will reset. Again, along the same line of you have to know what you're asking for. Like I showed you the pie chart, I'm going to split according to age. Does it make sense? No. It will give you results, but it does not make sense. What are you asking the computer now? You're asking SPSS to give you or to split the data into each different age, and ages 20 and 21 and 22 and 23. So it's a continuous variable. I cannot put a splitting variable as a continuous variable. If I click on OK, and then I ask the computer, give me the let's say systolic blood pressure average. Look at this. It gave you the average systolic blood pressure for those who are 19, for those who are 20, 25, 26, 27. You see how many? So for each separate age, it gave you an average systolic blood pressure. It does not make sense. Again, for every single analysis that you do, you have to understand what are you doing and why are you doing it, and employ some critical thinking of the results that you get. So data, split file, you do not split according to a continuous variable. Most of the times we split according to a categorical variable. I will reset and OK. So far, what we have taken are under analyze, descriptive, frequencies and descriptives. Under data, split and select. and under transform, compute, and recode. By doing this, you are able to carry out almost 90% of whatever you need. There are few things that are a little bit more sophisticated, but you do not need them at this point in time. What remains for this prolonged session is the inferential statistics. What is inferential statistics? We are done with the descriptive statistics, which is frequency, number percent for categorical, mean standard deviation for continuous, and now we move to inferential statistics. What is inferential statistics? Inferential statistics, again, you should have covered it in previous sessions, but I will briefly tell you that inferential statistics has two things that you can do. Either you can estimate a value or you can evaluate a hypothesis. Again, estimating a value through a confidence interval, evaluating a hypothesis through a p-value. I'm not going to go in details about the theory of both of them, but you can go to previous recorded sessions and watch the one that is specifically on inferential statistics. But the confidence interval, mainly we do 95% confidence intervals to estimate a population number, and the hypothesis is where you have a null hypothesis and an alternative hypothesis. If a p-value is less than 0.05, it means there is significant results. If it is more than 0.05, it means that there is no significant association. I would like to show you this because this will summarize everything that I want to talk about in the next half an hour or 45 minutes. And this is something we call bivariate analysis. I did not tell you about the previous analysis that we did, which is the descriptive statistics. We usually call it univariate analysis. What does univariate analysis mean? It means that I'm taking only one variable at a point. Descriptive statistics is dealing with one variable. So whenever I summarized or described the age of the patient, it was one variable. I reported mean and standard deviation. When I did the description for the sex of the patient, I reported number and percent for males, number and percent for females. It was one variable. Now for the inferential statistics, we are moving a little bit beyond the description. I want to do something we call bivariate analysis. Bivariate analysis, it means that I'm taking two variables at the same time. Two variables meaning that I have to see the association between variable 1 and variable 2. For example, before I give you the example, there are three different scenarios in the bivariate analysis. And you remember I told you before that all the analyses that you do are based on the type of variable that you do. So there are three scenarios based on the types of variables. You can have categorical variable, you can have categorical continuous variable, and you have continuous variable. I will start with the categorical. Assume you would like to see the association between hypertension and gender. What does it mean? It means I want to see who is more hypertensive, males or females. What I do is I do a test called chi-square. I'll show you how to do it, but before I do that, I would like to summarize the results. In other words, I want to see, logically speaking, it is a categorical variable, so we talk about percent. So if I tell you if a person is a male, they have 30% probability of being hypertension. If a person is a female, she has 30% probability of being hypertensive. It means whether a person is male or female, they have exactly the same probability of being hypertensive. Thus, we can say there is no association. If another scenario, I tell you if a male, they have 30% probability of being hypertensive, and if a person is a female, she has 60% probability of being hypertensive, you tell me females are more likely to be hypertensive because they have double the risk or double the chances or double the probability. So the way to represent this association, I do something we call 2x2 table. How to do it? I go to analyze, descriptive again. There is something we call crosstabs. If you look at the picture, it is like a table, and you see why, and you will see now why it is a picture of a table. If we click on this, there is the opportunity of putting two variables in the row and in the column. Assume that I'm interested in sex and hypertension, so I put sex in the row and hypertension in the column. I click on OK. This is what we call a 2x2 table. Why do we call it 2x2? Because there is yes, no, and male, female. 2x2. Now, does it mean that all of the tables are 2x2? No. It can be 3x2 if I'm talking married, single, widow, and male, female, whatever. So, what do I conclude here? I conclude that 191 people are males and non-hypertensive. 52 are males and hypertensive. 24 are females and non-hypertensive. 20 are females and hypertensive. I have 287 total, 243 males, 44 females, 72 hypertensive, and 215 non-hypertensive. Okay? But this does not answer my question. What is the probability of hypertension if the person is a male? What can I do? I'll do the following. I go to Analyze, Descriptive, Crosstabs. The same thing. But under Cells, I want to select row, column, or total. In here, I selected rows being sex, columns being hypertension. I want among the sex, meaning among the rows. So if a person is male, what is the probability of hypertension? I will select row. Look what happens. Continue and OK. It's exactly the same thing, but now I have the 191 and I have another percentage. What is this percent? Within sex, meaning if the person is a male, what is the probability of being non-hypertensive? It's 191 out of 243, which is 78.6. I'm not interested in non-hypertension. I'm interested in hypertension. So 52 out of 243 is 21.4. What about if a person is a female? If a person is a female, 20 out of 44, it's 45.5. What does it mean? It means that if a person is a female, she has double the chances of being hypertensive. Why? Because if a person is a female, she has 45% as compared to 21% if a person is a male, right? And this is exactly what I would report in a paper. In a paper, I would report 52 between two brackets, 21.4, 20, 45.5, but where is the inferential aspect of the analysis? I have to provide the p-value. What is the p-value? The p-value is the measure or the probability that tells me whether there is a significant association between gender and hypertension. Where do I get this p-value? Again, Analyze, Descriptive, Crosstabs. Under Statistics, we have the chi-square. And remember, bivariate analysis, categorical, we do a test called chi-square to be able to get the p-value. Where do I go now? I select chi-square, continue, and then I click on OK. It will give me everything I want to report in the paper. So I report 52, 21.4%, 20, 45.5%, and I look at the significance, which is the p-value, two-sided, and here you have Pearson chi-square, and it is 0.001. And as you know, that the cutoff point for the p-value to be significant is 0.05. And I found that this p-value is less than 0.05, thus it is significant. And the conclusion will be there is a significant association between gender and hypertension among those patients who are admitted with MI to the emergency department. Right? Now, assume that I want to do a full analysis. What is the full analysis that I want to do? I want to compare those who are smokers and non-smokers in terms of everything. Okay? So I'm writing a paper, the effect of smoking on outcomes of MI, myocardial infarction among emergency department admissions. Okay? So all the analysis that I want to do, I want to divide it according to whether the person is a smoker or not. Theoretically speaking, you would go to data, split according to, you remember what we just talked about, split according to smoking status, and I do all the analysis. But this split will not give you the p-value. I want the p-value of the association. So what do? I go to analyze, descriptive, crosstabs. I will reset. I'll change in the columns, I'll put smoking status, current cigarette smoking. But remember, we're talking about categorical. So this is a categorical. I don't put age here. Let me show you why. If I put age, look at this 2x2 table. You see it? It means nothing to me, right? You won't be able to understand it. Chi-square 2x2 table is only done for 2 or 3 or 4 by 2 or 3 or 4. So categorical. The two variables have to be categorical variables. I'll go again, analyze, descriptive, crosstabs. I don't ask for categorical variables. I ask for sex, marital status, hypertension, diabetes, family history of coronary artery disease, and so on. I put all the variables that are categorical in my data set. And finally, triage level, which is a categorical variable, and final outcome. What are the cells I want within current smoking? So I'm not going to ask for row percent, I will ask for column percent. Okay? Because I want to see if a person is a smoker, what is the probability of dying? If a person is a non-smoker, what is the probability of dying? I go to cells, I ask for column percent. And I go to statistics and I ask for chi-square. Again, just by you knowing what you are asking for, you'll be able to get all the results that you want. This is all the results. Let me go over a few of them. Sex and smoking. You see here, within current cigarette smoking. So it's not like this, because it's not within sex, it's within current cigarette smoking. So it's like this. So what is this percentage, which is this percent within current cigarette smoking? It is the probability of being a male if the person is a smoker. So 151 out of 158, 95.6. 92 out of 129 is 71.3. Is there an association between gender and smoking? Yes, it is very significant, 0.000. To make it more logical to you, let me go to the last one, final outcome. If a person is a smoker, what is the probability of dying? If a person is a non-smoker, what is the probability of dying? So 5 out of 159 is 3.1%. 5 out of 128, it's 3.9%. What does it mean? It means if a person is a smoker, they have lower chances of dying. Do not think of the clinical aspect of it. Again, this is a hypothetical data, so it might not make sense in everything, but what it's showing me here, according to the sample that I took, that 3.1% of smokers die, 3.9% of non-smokers die. But what's important is the significance. Is it significant? No, because it's more than 0.05. Thus, you can say there is no significant association between smoking and death among people who are admitted to the emergency with an MI. Okay? Another just quick example, let me take the hypertension. If a person is a smoker, 16.4% are hypertensive. Non-smokers, 35.9%. It's along the same line, right? More chances of being hypertensive if non-smokers. Is it significant? Yes. It means that smokers are significantly less hypertensive as compared to non-smokers. Okay? Now, you see all of these results? You'll be able to fill half of the table of table 1 from the manuscript, which is smokers, non-smokers in association with gender, with nationality, with hypertension, diabetes, prior history, and so on and so forth. So these results will be able to give you everything you want to fill half of the first table. Why did I say half of the first table? Because I did not talk about the other half or the continuous variables. We did categorical, which is smoking, yes, no, and the other categorical variables, which are gender and so on and so forth. But what if I'm interested in smoking and age? And this is where I move to the categorical and continuous variable. And under categorical and continuous variable, I have 4 tests to talk about. One of them is the one sample t-test, another is paired t-test, a third is independent sample t-test, and the fourth is the ANOVA. The one that will answer my question that I just asked you, which is smoking and age or smoking and systolic blood pressure, will be independent t-test. But to be systematic in my interpretation or explanation, I will go starting from the one sample t-test all the way to ANOVA. Let us go to the one sample t-test. Oh, sorry. This is the chi-square test. Okay, since it's there, I'll just explain it in 1 second. Sorry for the disruption, but anyway, chi-square test. Assume you're interested in hypertension and gender. As you might know that the p-value is related to a hypothesis test, and I always have a null hypothesis and an alternative hypothesis. The null hypothesis means that probability of hypertension among males is equal to the probability of hypertension among females. The alternative is that they are not equal to each other, and I calculate it through chi-square. Now, the second example for the one sample t-test, which I'm explaining now. I might have a question, is the systolic blood pressure normal, i.e., in other words, is the systolic blood pressure for patients admitted to the emergency with an MI considered normal? What is the normal value for systolic blood pressure? Assume it is 120. What would the null hypothesis be? It means it is the average systolic blood pressure for the whole population is equal to 120. The average systolic blood pressure for the whole population is not equal to 120. And I have to carry out a test, which is called a one sample t-test. But again, one sample t-test is under categorical continuous. Although I'm not dealing with 2 variables per se, but the same family of tests, which is the t-test, is used. Now there are 4 types of this family, or 4 members of this family. One sample t-test is when I have a continuous variable and I want to measure it in reference with a cutoff point or a certain value. So how do we do that? I'll go to the analyze, of course. There is something we call compare means. So what does compare means mean? You have the 4 tests that I will be talking about. You have the one sample t-test, the independent, the paired, and the ANOVA. I'll start with the one sample t-test. The one sample t-test, it's asking you, what is the test variable? What am I testing? If you remember the question, it was systolic blood pressure. So I want to go and select systolic blood pressure and put it here. So what is the value that I'm testing it against? It's the 120, right? So, okay, and I find this. Let us read the output. Sample size is 286. It means that I have 286 people who have valid information about their systolic blood pressure. The average is, okay, this is a mistake that I did. Look here. Do you expect an average systolic blood pressure of 2.27? No. Why did this happen? Because I took the systolic blood pressure categorical. It is the variable, categorical variable, which is 1 to 3. You remember when we created it? 1 meaning less than 120, 2 meaning 120 to 140, and 3 meaning more than 140. It gave me an average and the standard deviation, but it's wrong. So what I do is analyze, compare means, and one sample t-test. It's not this variable. Let me expand it a little bit. It's not the categorical variable. It is the systolic blood pressure, which is continuous. And now I have 286 people. The average is 144.13. The standard deviation is 35. Forget about the standard error. And this is the t-test that we have. All what I care about is the sig. What does sig mean? Significance. What is the p-value that I found? 0.000. What does it mean? It means that it is less than 0.05, meaning that it's highly significant. What is the p-value? What is the hypothesis that I'm testing? That the population has an average of 120 systolic blood pressure. But I find my patients to be 144, meaning they are way above the normal value. Thus, I can say it's highly significant. Again, let me give you another example. Assume that I know that in the States, the average age for patients admitted with an MI to the emergency is 65 years. Okay? I want to check whether in Lebanon, the average age of people admitted to the emergency is also 65 or not. So is there any significant difference in age between Lebanon and the States? What is the variable that I'm dealing with? Age. What is it? Continuous. Am I testing it against what? A fixed value. This should indicate to you that we are doing what? A one sample t-test. How do I do it? I go to analyze, compare means, one sample t-test, and I reset. What is the variable I'm testing? Age. What is the reference value that I'm testing? 65, which I got from the States. I click on OK, and I find that my patients in Lebanon, their average age is 52.6. Compared to 65, it's way below. What does it mean? Highly significant. So I can say that patients admitted to the emergency with an MI in Lebanon are significantly younger than those who are admitted in the States. Assume somebody comes to you and tells you, well, no, you're overestimating it. Or somebody brings a paper to you and tell you, well, the average age of people admitted to the emergency in the States is not 65. Is what? Let's say 54. So what do? You change this to 54, right? Click OK. I did this just to show you that 52 versus 54, it is lower. Is it significant? No. Why? Because the p-value is 0.076, and we have decided that the cutoff point for p-value to be significant is 0.05. Thus, it is more than 0.05, meaning it's not significant. And the conclusion will be the patients admitted to the emergency with an MI are not significantly different than the patients admitted to the emergency with an MI in the States. Okay? This is the one sample t-test. Again, we do the one sample t-test because it's a continuous versus a fixed number. Now, another example is called paired sample t-test. What does paired sample t-test mean? The concept of paired means that there should be a pair, right? Pair mean that the same patient, I measure something on that patient twice. For example, is the heart rate at admission different than the heart rate at discharge? So a patient is admitted to the emergency with a certain heart rate. I want to see whether their heart rate significantly goes down or goes up. Why is it paired? Because it's the same patient I'm measuring twice on them. That's why I call it paired. Why is it a t-test? Because it's a continuous variable that I'm dealing with, which is the heart rate. What is the null hypothesis? Heart rate before is equal to heart rate after. What is the alternative? Heart rate before is not equal to heart rate after. What do? The paired sample t-test. Let us go to the data. Again, analyze, compare means, paired sample t-test. So what is a paired sample t-test? Look at this. It asks you paired variables. I cannot put systolic and diastolic. Why? Because systolic is different than diastolic, right? Although they are two continuous variables, but they do not relate with each other. I have to do something that is before, after. Or, let me give you another example. If I measure systolic blood pressure in the right hand and in the left hand, both are continuous, both are measured on the same patient. This is why it's called paired. So, back to the example. I have heart rate at admission. I cannot click OK, right? Because I have to specify the second pair, which is heart rate at discharge. I click on OK. Look at this. It is telling me heart rate at admission is 81.16. Heart rate at discharge, it's 76.7 with the standard deviations. Is there a significant association? I look at the significant test without you worrying about how did I calculate the t-test and how did I get the degrees of freedom df, which you do not care about, and all what you care about is the p-value. The p-value is 0.133. What does it mean? It is not statistically significant, meaning that although the heart rate decreased or was reduced at discharge, but it was not significantly reduced, right? It was decreased by 5 units, but this 5 units decrease is not statistically significant. Okay? Now, I don't have another example in this data set to show you for paired, but just want you to remember, a paired t-test is always done when you have a measurement done on the same person at 2 different points in time or at 2 different ways. So I can take, let's say, blood pressure while standing and while sitting. It's the same person. So if I want to compare the systolic blood pressures, I do a paired t-test. Again, I go to my slides. So one sample t-test is when I compare a continuous variable with a fixed number. Paired t-test is when I compare 2 continuous variables before, after, or left, right on the same person. The most frequently used t-test is the independent sample t-test, which is relating to this. This is smoking and gender, smoking and death, smoking and hypertension. Here I want smoking and age, smoking and systolic blood pressure, smoking and heart rate, and so on. So it's called independent t-test. It's similar to the t-test here, but this is paired, meaning the same person. This is independent, 2 groups. So who are the 2 groups here? Smokers, non-smokers. Now, let me go to the data. How do I do that? Analyze, compare means, independent samples t-test. So it's not paired samples being the same person, independent samples. So the smokers are completely different than the non-smokers. They are not the same people. So I do not deal with paired, I deal with independent samples. Independent samples t-test, of course, if you look at this, you have categorical, continuous, right? Let me, now I have an example here. So categorical, continuous, independent sample t-test. Is systolic blood pressure different between males and females? What is the null hypothesis? Systolic blood pressure average among males is equal to the systolic blood pressure among females. If I tell you the average systolic blood pressure among females was found to be 130 and for males is 130, what do you conclude? There is no difference. The alternative hypothesis is that the systolic blood pressures are different from each other. What do I do? Independent sample t-test. What is the test variable? It's the continuous variable. What is it? Systolic blood pressure. Make sure it's not the categorical continuous. It's not the categorical blood pressure. What is the grouping variable? It is the categorical variable. In this example, it is the sex of the patient. I still cannot click on OK. Why? Because you see these question marks? SPSS wants you to specify what are the 2 values for sex. Although I only have 2 values for sex, which is 1 and 2, but it wants you to specify what they are. Because what if I put something like marital status, married, single, widow, 3 groups? It doesn't work. It asks you to specify only 2 groups. So in this case, I put defined groups. The first group is 1, the second group is 2. Why? Because 1 is male, 2 is female. Continue, and okay. This is the output. The output is the following. Again, 145 is the average systolic blood pressure for males. 138 is the average systolic blood pressure for females. You remember when we split? If we split according to the gender and then get the average systolic blood pressure, this is what we will get. But the only difference in the split, I will not get the p-value. Here, I will get the p-value. Okay? So, what I did was independent samples t-test, and accordingly, I was able to get the average systolic blood pressure for males, average systolic blood pressure for females, with their standard deviations, and I can structure the table that I want to put in the manuscript or the report. The important thing is the p-value. Now, the p-value is here in this table. It's a little bit complicated. I'll try to simplify it as much as possible, but I would like you to understand the difference between these two things. What am I doing here? I'm testing the equality of what? Of means, right? I'm seeing whether the averages or the means between the males and the females are equal to each other. So I'm testing for equality of means. It's the same way why I decided to go compare means, right? I compare means because I want to test equality of means. Now, under this section, there is sig two-tailed, meaning the significance, meaning the p-value. There is 1 and 2. 1 and 2. So which one do I take? The one that I take is dependent on this. You see this test? It's not equality of means, it's equality of variances. Why do I need it? I need it because, look at these two. 0.269, 0.278. What's different between them? You see here, equal variances not assumed. So, I have two I have two p-values for the means. One when equal variances are assumed, another one when equal variances are not assumed, meaning one p-value when we have equal standard deviations, to simplify it. Another one when I don't have equal standard deviations. Why is it complicating it that much for us? Because the p-value for this test could be calculated by two formulas. One, when we assume standard deviations are equal. Another one, when the standard deviations are not equal. So, if I end up deciding that the standard deviations are equal, then I take this p-value, right? If I end up deciding that equal variances or standard deviations are not equal, then I take this p-value. I might have confused you with the standard deviation and variance, but again, you should have taken this in previous session, but the variance is square the standard deviation, or standard deviation equals square root of variance. That's why I interchangeably using both. Again, consider this as a standard deviation. If I end up assuming that the standard deviations are equal, I report 0.269 as a p-value. If I end up deciding that the standard deviations are not equal, I use 0.278. So the question now becomes, am I going to consider the standard deviations equal or not equal? This is where I test for equality of variances or equality of standard deviations. Okay? Does it ring a bell? I'm checking whether variances are equal or variances not equal. So I'm checking equality of variances now. Where do I get it from? This. Equality of variances. So what is the test that I'm using here? It's called F-test. You don't care about it. What you care about, the p-value. The p-value for what? For the F-test. What is the F-test testing? The equality of variances. What do I find it to be? 0.835. What do you conclude? No significant difference. If no significant difference, are they equal or not equal? Equal. So if they are equal, you take this p-value. Now let us assume that it is 0.001. This p-value 0.001. What does it mean? It's statistically significant. What is it testing? Equality of variances. What does it mean? There is a significant association or significant difference between the variances or the standard deviations. What do you conclude? They are not equal. What do you report? 0.278. Okay? Now, as a summary, when do we use independent samples t-test? Whenever I have a categorical and a continuous variable. Okay? How do I do that? And let me summarize it with another example. You remember here when we put smoking smoking and gender smoking and death smoking and so on and so forth, I want to continue the other half of the table that I told you about, which is smoking and age, smoking and systolic blood pressure, smoking and so on, right? So what is one variable? Categorical. What's the other variable? Continuous. Are they dependent on each other? No. So that's why we use independent t-test. What do? I go to the data, analyze, compare means, independent samples t-test. Reset. What is the categorical variable that I'm using? Smoking. Current cigarette smoking. What are the two values? I don't remember. Let me guess. If it is 1 and 2, I just want to highlight something for you. And what is the continuous variable? It's age. So continuous variable, categorical variable. I click on OK. It tells me the independent sample tables is not produced. Why? Because yes is 1, but there's no 2. There are 0 people who have 2 current smoking. Why? Because current smoking is done as 0, 1, not 1, 2. Okay? So I go back to my analyze, compare means, independent samples t-test. I click here. It is 1 and 0. Continue. And now I get the average age for smokers is 47. The average age for non-smokers is 59. So smokers are younger. Can you see this from these two numbers? Smokers have younger age, 47 versus 59. Is the association between age and smoking significant? Yes, both of them are the same p-value. In other words, you report less than 0.0001. SPSS does not give you a long p-value. The maximum or the minimum p-value that it will give you is 0.000. What you know is that it is less than 0.0001. You don't know exactly how much it is, but you will report it as less than 0.0001. That's why in papers, if you open a paper, you might find sometimes for highly significant associations, p-value of less than 0.0001. 3 zeros. Now, both of them are equal to each other, but let us go through the exercise. Which one do you take, this or that? You look at the equality of variances. 0.04 less than 0.05, meaning significant, significantly different from each other. Equality variance is not assumed, thus you take the second one. Okay? Now, the same thing as I did with the chi-square, I can do compare means independent. I can select all the continuous variables. You remember when I told you in one step you get half of the table, and in another step you'll get the other half of the table. Okay, and this is duration of emergency, and there you go. In this, you'll be able to see what is the average age for smokers, non-smokers, average weight for smokers, non-smokers, average duration of symptoms, smokers, non-smokers, average respiratory rate, smokers, non-smokers. So you get all the results you have to put in the table. What about the p-values? The same thing. This is the p-value. This is the p-value for weight, 0.41 or 0.40. You look at this and you decide. So these are the p-values for all of them. So as a summary, in 2 steps, you will be able to get the association between a categorical variable and many categorical variables, a categorical variable and many continuous variables. Let me give you an example, a practical example now. Assume you do a clinical trial. You allocate or you randomize people into 2 drugs, drug A and drug B. And eventually you collect information about their age, their gender, their hypertension, their diabetes, their blood pressures, their weight, and so on and so forth. So you collect so many information on them. When you reach a place where you want to analyze the data, there are 2 tests that you will be using. You want to compare drug A to drug B. So it is a categorical variable. If you want to compare a continuous variable with this drug A, drug B, you use an independent t-test. If you want to compare gender between drug A and drug B, you do it by chi-square. So all the analysis that you will have to do, you'll have to do it in 2 steps. 1 step through chi-square, drug A, drug B, and all the categorical variables. And another step by t-test, meaning drug A, drug B, categorical, and all continuous variables. Once you do these two steps, you would have done all the bivariate analysis. There are two more things that I want to give you, which is the ANOVA and the correlation coefficient. What is the ANOVA? ANOVA is exactly the same as the independent sample t-test. But you remember when I told you what if we want to compare systolic blood pressure for married single widow? We said that we cannot do more than 2 groups for the independent samples. So you have to specify males, females, or married single, or married widow, or widow single. ANOVA is exactly the same as the t-test, but instead of having only 2 groups, I have more than 2 groups. So I can compare a continuous variable with a categorical variable, but the categorical variable has more than 2 groups. Let me go back to this outline. Categorical continuous. If it is categorical 2 groups only, like smokers, non-smokers, or male, females, or drug A, drug B, I do independent sample t-test. If I have 3 groups or more, such as drug A, B, or C, I do ANOVA. So both t-test and ANOVA are done for categorical continuous. The only difference between them, independent t-test is the categorical has to do 2 groups. In ANOVA, it can be 3 or more groups. Okay, let us go to actually the example that I have for you here is ANOVA. Is systolic blood pressure associated with triage level? What is triage level? We didn't talk about it so far. Let us go for a frequency distribution. Triage level is here. Triage level, I guess all of you know what triage level is. It's the severity of the case of the patient at admission, and it ranges between 1 and 4. So this is a categorical variable, 1, 2, 3, 4. I want to compare the systolic blood pressure for group 1, group 2, group 3, group 4. Can I do a t-test, independent t-test? No, because if I want to do an independent t-test, I have to select only 2 groups, but I want to compare the 4 of them. What do? I go to analyze, compare means, but it is called one-way ANOVA. And it's a summary of analysis of variance. So ANOVA, it's exactly the same layout. You have the continuous variable, the categorical variable. What is the continuous variable? Systolic blood pressure. What is the categorical variable? It is the triage level. Does it ask me what are the 2 values? No, because even if it's more than 2 values, it takes it, right? And the independent sample t-test, it told me what are the 2 levels that you want, because I have to specify. Now it does not ask me. I have to ask for options descriptive. Why? I want the mean and standard deviation. I click on OK, and eventually this is what I get. For triage level 1, the average systolic blood pressure is 142. For triage 2, it's 147. Triage 3 is 132. Triage 4 is 129. So you see how it changes with the different triage levels? Now the question is there any significant association between triage levels and systolic blood pressure? You look at the p-value. What is it? 0.073. Is it significant? No, it's not. So you can say there is no significant association between triage level and systolic blood pressure. Now, the last thing I want to give you is, what if we have a continuous? Assume you want to see the association, or before I do that, we do a test called correlation. The continuous, assume you want to see whether systolic blood pressure is associated with height. Both of them are continuous variables. I cannot do a chi-square. I cannot do a one sample t-test or an ANOVA or a paired sample t-test or an independent sample t-test. I have to do something we call correlation. Again, you have to remember that in the previous session we talked about correlation, and a correlation coefficient is a value that tells you whether there is a positive, negative, or no association between two continuous variables. It ranges between -1 and +1. -1 means a perfect negative correlation. A +1 means a perfect positive association. And the 0 means there is no association. Thus, the null hypothesis is that the correlation coefficient is equal to 0. The alternative hypothesis is that the correlation coefficient is not equal to 0. What I do is I go to the data. I opened something that I should not have opened. Okay. All right. So let me go back to the data. Before I see that, what I do is I do something we call scatter plot. Scatter plot is a graph that plots the two continuous variables so that we can visually see whether there is a positive or a negative association. A simple scatter plot is like this, and I can put two variables. As weight increases, does systolic blood pressure increase or decrease? This is systolic blood pressure. So I'm seeing the change in X with the change in Y. Both of them are continuous variables. So let us see what it looks like. Here you can see there's no perfect association, but you can see as weight increases, what's happening with systolic blood pressure? There is a little bit of an increase. You see it? A little bit of an increase. Is this increase significant or not? We do correlation coefficient. Where do I go? Analyze, correlate, bivariate. So, correlate bivariate, I enter two continuous variables. This is weight and this is systolic blood pressure. I click on OK. Look at this. It's telling me this is weight and weight. Two continuous variables. Are they correlated? Of course they are. Right? It's the same variable. That's why, what's the correlation coefficient? It's 1. It's perfect correlation. But this does not make any clinical sense. What I have to look for is systolic blood pressure and weight. Continuous, continuous. What is the correlation coefficient? It's 0.113. Okay? We said that positive, if the value is positive, it means that as one increases, the other increases. If it was negative, as one increases, the other, what happens with it? Decreases. If it is equal to 0, as one increases, the other does not change. Okay? What is the p-value? 0.059, meaning 0.06, meaning more than 0.05, meaning there is no significant association between weight and systolic blood pressure. Now, what is this cell? It's exactly the same. Here it's testing the association between weight and systolic blood pressure. Here between systolic blood pressure and weight. It's exactly the same. The same values, the same p-value, the same everything. Okay? Now, the same as I told you with the chi-square and the t-test. Look what you can do. Correlate, bivariate. Assume you want to see the effect of age on all the continuous variables. I put age, put weight, put height, put body mass index. Of course, all of them are continuous, right? Heart rate, and all of these. And I click on OK. Look what happens. You see this? It's a huge correlation table. Let us see what we're looking at. Age. Age and age, I don't care about it. Age and weight, negative. What does it mean? As age increases, weight decreases. Is it significant? Yes. Right? Age and height, negative. As age increases, height decreases. Is it significant? No. Age and BMI, negative, but significant. Age and heart rate at admission. As age increases, the heart rate increases. Not significant. Systolic blood pressure. There is almost no association. You see how close it is to 0? The correlation coefficient is 0.0, although it's positive, but it's very close to 0. And it's not significant. And what else? Diastolic blood pressure, minus 0.051, meaning that there is a negative association, but very close to 0, not significant. And so on and so forth. Right? So as a summary again, as a summary, you have this to keep in mind. You have to keep this in mind. Bivariate analysis, whenever you have categorical, you use a chi-square. Whenever you have categorical continuous, most of the times you do independent t-test. Why do you do independent t-test? Because they are independent and it's only two groups. If you have independent and more than two groups, you use ANOVA. If you're doing paired, the same person, you do paired t-test. And if you're measuring one continuous with a fixed number, you use one sample t-test. But most of the times, it is chi-square independent t-test. Finally, two continuous variables, you use correlation. Now, let me take a few minutes just to show you a few practical examples. I want to show you this. This is a paper about the association between near target caloric intake in critically ill patients and its association with adverse outcomes. It was published in Journal of Parenteral and Enteral Nutrition. And what we did in this example, we have three groups. Caloric intake was divided into three groups. Less than 33.4%, between 33.4 to 64% requirement, and more than 64. All what I care about to tell you now is that we have three groups. Categorical variable, right? Is it two groups categorical variable? No, three groups. You see all this table? It's all done with two tests. You should be able to decide or to know that the two tests we've done here are chi-square and ANOVA. How did we get the sex? I report 48 people out of the 170, 28.2%. 44 out of 181, 24.3%. 40 out of 172, which is 23.3%. Look at them. Are they different? No, 28, 24, 23%. Are they statistically significant? P-value is 0.54. What does it mean? There is no significant association between gender and the caloric intake requirement. Okay? How did we calculate this? By chi-square. What about age, or let's say BMI? The average BMI is 28.2, 26.6, 27.3, right? With the standard deviations. Is there any significant association? No, because 0.14. How did we calculate this p-value? By ANOVA, right? The same thing applies to all other variables. Average daily enteral calories. Diabetes history. This is categorical. There is a significant association. How did we do that? By chi-square. Let me go to the outcomes. ICU mortality. 12.4% died in this group. 13.3% died in this group. 22% or 20% died in this group. What do you conclude? There is a significant association. How did I calculate that? By chi-square. What about length of stay? How long did the person stay? In this group, 6.1 days, 10.5 days, and 13.9 days. Continuous variable versus categorical ANOVA. Okay? Let us look at the statistical analysis section. This is the statistical analysis section. We did it through another program called spss, statistical analysis software, but we could have done it through SPSS. But what I want to highlight is, look at this. Baseline characteristics for the three tertiles, meaning the three groups, but categorical variable, was done by the chi-square for categorical variables and the ANOVA for continuous variables. This is exactly what I explained to you now. I told you categorical plus categorical chi-square, categorical plus continuous is ANOVA, right? Now let us take another example. I'll take this paper. It's another clinical trial that we did on intensive versus conventional insulin therapy. It's a randomized controlled trial. The point is that we have two groups, drug A, drug B, or intensive insulin therapy or conventional insulin therapy. Again, You see all this table was done through 2 steps. Age continuous, categorical, 50.6, 54.3, significant difference. How did I do that? By independent sample t-test. Why? Because continuous variable age, categorical variable group, and it's 2 groups. What about female gender? 66%. Number, percent. P-value, not significant. How did I do that? chi-square. The same thing with the outcomes. Look at the outcomes. The outcomes, how many people died? 13.5% died in this group, 17.1% died in that group. What is the p-value? 0.70. What does it mean? No significant difference. Let us look at the statistical analysis section. The statistical analysis section is over here. We did baseline characteristics and outcome variables were compared using t-test, chi-square, forget about this, as appropriate. Why did we say as appropriate? Because the baseline characteristic, if it was continuous, we did a t-test. If it was categorical, we did a chi-square. Okay? So I did all of this to just show you that even if you're doing a complicated analysis, a clinical trial, it all boils down to 2 types of analyses. Categorical continuous or categorical or categorical continuous. This is the bivariate analysis. One last thing that I will be talking about, and we will end up this session, and it is something we call multivariate analysis. So at the beginning I talked about univariate analysis, which is 1 variable, description, number, percent, mean, standard deviation. Then we spent some time on the bivariate analysis, which is associating 2 variables, categorical continuous, and continuous. And the tests are chi-square t-test or correlation coefficient. Now, multivariate analysis is a set of analyses that we do whenever we are doing more than 2 variables. And again, in one of the sessions before, you should have taken the concept of confounding. Confounding is a concept where the 2 or the association between, let's say, mortality and intensive insulin therapy that I just talked about is affected by age. Why? Because those on one drug are older or younger. That's why they are dying more or less. So that's why we want to get the pure effect or the adjusted effect of the intensive insulin therapy or drug A or the new drug or whatever on mortality, while I remove the effect of age and the other confounders such as age and gender and so on and so forth. So again, if you do not grasp the concept of confounding properly, you will go and attend one of the previous sessions. Okay? So you have the multivariate analysis. You have 2 types of multivariate analysis. One is called logistic regression and another is called linear regression. What is logistic regression? Logistic regression is the analysis when the outcome is 2 levels, meaning categorical variables. So if the outcome is mortality and I want to do the association of the group drug A, drug B and mortality, but I want to control for age and gender and physical activity and family history and so on, I do logistic regression because the outcome is categorical. Logistic regression. Now, linear regression is when the outcome is continuous. So assume that I want to see the effect of the drug that I give on the length of stay in the hospital. Length of stay in the hospital is a continuous variable. So I cannot do logistic regression. I do linear regression, and thus I can relate the effect of drug on the length of stay of the hospital, in the hospital, while I'm controlling for age and gender and physical activity and family history and so on and so forth. Thus, multivariate analysis is used for adjusting for confounding variables. And just a brief introduction about it, I'll show you how to do that. Under analyze, you have something called regression. You have something we call linear regression and something we call binary logistic regression. We said binary logistic regression is where the outcome is categorical, Linear regression is where the outcome is continuous. I'll start with the binary logistic. The dependent, which is the outcome, let us say it's the final outcome, meaning that it is mortality, yes, no. And the covariates are being, let us say, age, sex, marital status, body mass index, hypertension, diabetes. And you see that I'm not linking one variable to the outcome, I'm linking many variables to the outcomes. And eventually I will do this, the following, and look what I get. I get the effect of age on death, the effect of sex on death, effect of marital status on death, hypertension on death, and so on. And these are the odds ratios. I did not cover the odds ratios, but you should have taken it in many of the previous sessions, in cohort studies, in case control studies, in theoretical statistics session, and so on. But here it means that body mass index increases the risk of death, and the p-value here is significant, whereas all the others are not significant. And this is where I have controlled for the effect of all the other variables. So for example, I can see the effect of body mass index on mortality is 1.52 odds ratio, but this 1.52 is controlling for the effect of age, sex, marital status, hypertension, and diabetes. And this is why we call it multivariate analysis, because I can see the pure effect of one variable on the outcome, which is mortality, while I control for the confounding effect of so many other variables. What if the outcome is continuous? I go to regression. I go to the linear regression. The dependent now is not categorical, is continuous. Let us say BMI is my outcome, and I want to see what's the effect of age on BMI, sex on BMI, and hypertension on BMI, and diabetes on BMI. Under options, I ask for the 95% confidence interval, and what I get here is the following. I have, as age increases by 1 year, body mass index decreases by 0.047 units. Okay, is it significant? No. As sex increases, meaning females compared to males have lower BMI, and this is something we saw before. Hypertension or hypertensive people are having lower body mass index because it's negative. It's similar to the correlation coefficient, but now it's multivariate, meaning that this effect of age on body mass index is controlling for all the other variables. And these are the p-values. I know this is overwhelming, but this is an introduction to the multivariate analysis. Eventually, you might take a whole course on just linear regression or logistic regression. This is just a very brief introduction about the multivariate analysis. Let me see if I can show you an example of linear or logistic regression. And this is a third paper that I will just show you. Cirrhosis. Okay. Okay, no, I think it's gonna take me some time, so I'll forget about it. And you can see any of the papers that are published in the literature. You can either find multivariate linear or logistic regression. And if you have any questions, please let me know. No, really, if you have any questions, so I can, maybe I have missed something. No? No? All right, so I hope this was helpful, and you know my extension, my email, you can refer to me for any further clarification, and I hope this was a good session. Thank you very much. الله يعافيك.